In this video, we're going to work on problem 2x3x2 from the textbook. Prove that each of the following sequences is convergent and find its limit. In the first part, the sequence is given by this. A1 is 1 and an plus 1 is an plus 3 over 2 for n greater than or equal to 1. The second sequence is given by a1 is equal to the square root of 6 and an plus 1 is equal to the square root of an plus 6 for n greater than or equal to 1. The third sequence is given by an plus 1 is 1/3 of 2an plus 1 over an square for n greater than or equal to 1, and a1 is a positive real number. Finally, the fourth sequence is given by an plus 1 is 1/2 of an plus b over an for n greater than or equal to 1, and again a1 is a positive number, b is a positive number as well. Before solving the problem, let me recall some important facts. A sequence an of real numbers is called increasing if an is less than or equal to an plus 1 for all n in n. Okay, so over here we look at sequences of real numbers. A sequence an of real numbers is called decreasing if an is greater than or equal to an plus 1 for all n in n. And now if we replace this inequality by a strict inequality, that is an is strictly less than an plus 1 for all n in n, then we say that an is strictly increasing. Similarly, we can define what it means by an is strictly decreasing. Now I'm going to recall a very important theorem in this section. It is the monotone convergence theorem. If a sequence an of real numbers is monotone increasing and bounded above, then it is convergent. And similarly, if an is monotone decreasing and bounded below, then it is convergent. Now we are ready to solve the problem. In the first part, the sequence is given by a1 is equal to 1 and an plus 1 is equal to an plus 3 over 2 for n greater than or equal to 1. Okay, so let's try to find some elements of this sequence. So for sure, a1 is equal to 1. Okay, what about a2? a2 is equal to 1 plus 3 over 2. So a2 is equal to 2. What is a3? a3 is equal to a2 plus 3 over 2. So this is 2 plus 3 over 2, and this is equal to 2.5. Okay, and similarly we can find other elements of this sequence. Let us first show that an is strictly increasing. Obviously, a1 is equal to 1, so it's less than 2, that is a2. Okay, and our goal here is to show that an is strictly less than an plus 1 for all n in n. Okay, and this is true when n is equal to 1. Okay, now we suppose that ak is strictly less than ak plus 1 for a positive integer k. Okay, this is the inductive hypothesis. And now we're gonna use this inductive hypothesis and the given formula for the sequence to prove that ak plus 1 is less than ak plus 2. Then from this inequality, we can add both sides by 3. So then ak plus 3 is less than ak plus 1 plus 3. Okay. And hence, we can also divide both the sides by 2. So ak plus 3 over 2 is strictly less than ak plus 1 plus 3 over 2. Now, this implies that ak plus 1 is strictly less than ak plus 2, because this is exactly ak plus 1 and this is exactly ak in plus 2. Okay, so by induction, we see that an is less than an plus 1 for all n in n. Therefore, an is strictly increasing. Next, let us show that an is less than 3 for all n in n. That means an is bounded above by 3. Okay? For n equals 1, a1 is equal to 1, so it's strictly less than 3. Okay? Again, here we apply the mathematical induction to prove that this is true for all n in n. Now, suppose that ak is less than 3 for a positive integer k. Then, by the definition, ak plus 1 is equal to ak plus 3 over 2, so it's strictly less than 3 plus 3 over 2, that is 3. Okay. By induction, an is less than 3 for all n in n, and so an is bounded above by 3. Okay. We have proved that an is monotone increasing and bounded above by 3. So by the monotone convergence theorem, an is convergent. Okay. Now, because an is convergent, we can define L as the limit of an as n approaches infinity. Okay. And now, as you know, an plus 1 is an plus 3 over 2, because an, the limit of an as n approaches infinity is L, the limit of an plus 1 as n approaches infinity is L. Okay. And by the limit theorem, we see that L is L plus 3 over 2. And so we can easily solve this equation and get that L is equal to 3. Okay. So the limit of an as n approaches infinity is 3. The solution for the second part is very similar. We can show that the sequence an is strictly increasing and also bounded above by 3. And then we can apply the monotone convergence theorem to conclude that the limit of an as n approaches infinity exists as a real number, and the limit is actually 3. Okay. Now I'm going to focus on the third part of the problem, where the sequence AN is given by this formula. To solve the problem, let me recall a very important inequality. For three non-negative numbers A, B, and C, A plus B plus C over 3 is always greater than or equal to the cube root of A times B times C. So this is the mean of three non-negative numbers. And this is the geometric mean of three non-negative numbers. So the conclusion is the mean of these numbers is always greater than or equal to the geometric mean of the numbers. And the equality holds when A is equal to B and is equal to C. This inequality works for n non-negative numbers as well, okay? But for solving this problem, we only need this inequality, okay? So now, for n greater than or equal to 1, an plus 1 can be written as this: 1/3 of 2an plus 1 over an squared. So this is equal to 1/3 of an plus 1 over an squared. Okay? So this is the mean of three numbers, an, and 1 over an squared. The mean of these numbers is greater than or equal to the geometric mean of these numbers. So this is greater than or equal to the cube root of an times 1 over an squared, and this is exactly 1. Therefore, an is bounded below. Okay? And in the next step, we're going to show that an is monotone decreasing. Now we're going to form the difference of an plus 1 and an to see whether an is monotone decreasing or not. Okay? So we have this. An plus 1 minus an is equal to 1/3 times 2an plus 1 over an squared minus an. Okay, so we can easily see that this is equal to 3an squared, and at the bottom and on the top, this is 2an to the third plus 1 minus 3an to the third. Okay, and this is 1 minus an to the third over 3an squared. Okay. So from the definition, because a1 is positive, you can easily show by induction that an is greater than 0 for every n. And in the first part, we already showed that for all n greater than or equal to 1, an plus 1 is greater than or equal to 1. Okay. Therefore, a2 is greater than or equal to 1, a3 is greater than or equal to 1, and so on. Okay. So starting from 2, we see that an to the third is always greater than or equal to 1. Therefore, this is always less than or equal to 0 for n greater than or equal to 2. Okay. So from here, we will see that an plus 1 is less than or equal to an for all n greater than or equal to 2. Okay. Then we can apply the monotone convergence theorem. Observe that over here we only need to care about all n greater than or equal to some positive number n naught, and over here is 2. Okay. We have proved that an is monotone decreasing and bounded below by 1 starting from the index n naught equals 2. So by the monotone convergence theorem, an is a convergence sequence. Okay, and we can let L be this. L be the limit of an as n approaches infinity, because we already showed that an is greater than or equal to 1 for all n greater than or equal to 2. So by the comparison theorem, L is greater than or equal to 1. Okay. In addition, we have this. As you know, an plus 1 is 1/3 of 2an plus 1 over an squared. So by the limit theorem, we have the following equation. L is equal to 1/3 of 2L plus 1 over L squared. Okay. So we're going to find L by solving this equation. So we multiply both sides by 3. So we get 3L is equal to 2L plus 1 over L squared. And then we can multiply both sides by L squared as well. So we get 3L to the third is equal to 2L to the third plus 1. So L to the third is equal to 1, and L is exactly 1. Okay? Therefore, the limit of an as n approaches infinity is equal to 1. Okay. For the fourth part, the solution is very similar to the third part. So we can apply this inequality for two non-negative numbers to show that an is bounded below, and then we can show that an is in fact monotone decreasing and apply the monotone convergence theorem.